Hi guys, this is Ms. Romani once again, and this week we're starting our final unit for this course, homeostasis. What is homeostasis anyway? Well, the term homeostasis was actually first defined in the mid-1800s as the tendency that living things have of maintaining a relatively constant internal environment. So what does that mean? Well, let's take humans for example. The human body is able to keep a relatively constant internal temperature between 35.6 to 37.8 degrees Celsius. And we can usually maintain this temperature range no matter what is happening to the external environment. That means that if it gets too cold or too hot outside, we will respond in ways that will keep our body temperature somewhere within that range. Like for example, by shivering or sweating. Similarly, we can adjust to keep our blood volumes steady and our blood sugar levels steady. Why is homeostasis so important? Why do we need to keep our internal conditions within a narrow range of values? Well, to answer this, let's talk about what happens when we go outside of these range of values. By the way, these sets or values are also called set points, normal range that the body tries to stay within. For example, let's take what happens when our temperature drops below 35.6 degrees Celsius. If that happens, we enter a state that is described in medicine as hypothermia, which can be dangerous and can lead to death. A drop in blood volume, on the other hand, can lead to severe dehydration, and a drop in blood sugar levels to a condition called hypoglycemia. All of these can be extremely dangerous and can lead to death if untreated. So in short, homeostasis helps to keep us alive. When conditions move outside the set point range, the body is brought back into balance via homeostasis. If homeostasis cannot be restored, however, then that can lead to disease and even death. So a good analogy to help us understand homeostasis is your home furnace. The way your furnace works is that somewhere in your house, maybe close to the living room, somewhere visible, you have something called a thermostat. And that thermostat also has a thermometer. The thermostat can be set at a desired temperature. So for example, this one is set at 70 degrees Fahrenheit or 21 degrees Celsius. So this would be the set conditions. If the thermometer in the thermostat detects that the house has dipped below the set temperature, then a message is sent to the furnace, typically in the basement of the house, to turn on and start pumping out heat. Once the house warms up and the thermometer on the thermostat detects that the set temperature has been reached, then a message is sent to the furnace to turn off, and it will essentially stay off until the house cools off enough so that the set temperature is once again achieved. A similar but opposite system happens in the summer, but instead of the furnace, it turns on and off an air conditioning unit if you have one. So this type of system is what we call a negative feedback loop. Negative feedback loops are meant to restore conditions back to their original or their set state. So homeostasis in the body is basically maintained using negative feedback loops like the one I just described. They start with a stimulus and they have three main components. In the previous example that I just gave you, the one about the furnace, the stimulus would be a drop in temperature. The first component of the negative feedback loop is what we call the sensor. The sensors basically detect conditions or changes to the set conditions. So in the home example, the sensor would be the thermometer that would detect when the temperature drops below the set temperature. Once this change is detected, a signal is then sent to what is called the control center, which is basically in charge of comparing the conditions detected by the sensor with the conditions that were set as optimal. So in the previous example, the control was the thermostat, and it basically compared the temperature that was set on the thermostat by the family against the temperature that the thermometer was saying that the house was at. And last, we have what is called the effector. The effector is basically the response. It could be one response or it could be many more responses by the system that is used in order to restore conditions back to the set conditions. And so the control center will communicate with the effector, and in the home example, the effector was the furnace. So now let's compare all of this to how our body controls temperature. So let's say we have a stimulus. Let's say the stimulus would be that you get too hot. Your body temperature exceeds now the set temperature of 37 degrees Celsius. A sensor, nerve cells that we have in both our skin and that communicate with our brain, will detect that the temperature in our body has increased. That information is sent to the control center, and for body systems, most of the time, the control center is the brain. And in this particular case, a particular part of the brain that controls our body temperature. And then once the brain determines that the set temperature has been exceeded by the temperature detected by the sensors, then it's going to send information to an effector. And in this particular case, the effector could be the sweat glands that are on our skin throughout our body in order to reduce body temperature, hopefully back to the set conditions. So this is a very simple example of a negative feedback loop. You saw the example with a home furnace, and now I'm showing you the same example, but with a human body. And once again, you have to have a stimulus to begin the process, but the system itself is dependent on three components: a sensor, a control, and an effector. And we're going to look at many negative feedback loops in this course. Well, negative feedback system loops basically return conditions to the set conditions of the system. Positive feedback loops basically do the opposite. Positive feedbacks are there to amplify a small effect into a much bigger effect. They're basically the opposite of homeostasis. Homeostasis is achieved by negative feedback systems. Positive feedback systems will throw a body off of homeostasis. So since living things are there to try to achieve homeostasis, we don't find a lot of positive feedback loops in body systems. So they're very rare in living things. However, they're quite common in nature. For example, when we take a look at climate and climate change in particular, there's a whole bunch of positive feedback loops that unfortunately feed into the system. Let's say we start with increasing carbon dioxide levels in the atmosphere. The increase in carbon dioxide in the atmosphere basically leads to a warmer atmosphere, as carbon dioxide traps the heat closer to the earth. But a warm atmosphere will in turn warm the oceans. Warmer oceans can hold less carbon dioxide. A lot of the carbon dioxide that is on Earth is actually dissolved in ocean water. But when ocean water gets warm, it releases more carbon dioxide gas. And that's because warmer water cannot hold gas as easily. As the ocean waters get warmer, there's less uptake of carbon dioxide gas. That means that more carbon dioxide gas ends up in the atmosphere, which in turn warms the temperatures even more, which in turn warms the oceans even more, which means that the oceans can hold even less carbon dioxide. And as you can see, that's what we call the positive feedback loop. Every event amplifies the previous one, so then the event basically becomes more and more amplified. On the left, you can see, again, another example that deals with climate change. So these are positive feedback loops. Not great news for the environment and for climate change. So let's talk about the body. Where can we see positive feedback loops in the body? So one of the few examples of a positive feedback loop in humans occurs when a woman goes into labor. This is not a process that requires homeostasis. That would actually involve keeping the baby in the womb, because that would be the set conditions. The aim of labor is the opposite of homeostasis, is to get the baby out. So the aim is actually to increase contractions so that the cervix, which is the opening at the bottom of the uterus, can then dilate about 10 centimeters, which will be big enough for the baby's head to pass through into the birth canal and be born. So prior to the onset of labor, usually about a week or so before labor, the baby changes position so that it's head down. And then a few days before labor begins, the baby drops. And that just basically is a term that is used for when the baby's head drops lower into the pelvis. And this pushes the baby's head against the opening of the uterus, which is the cervix. And this is a stimulus that actually starts the process of labor. The head of the baby pushing against the cervix sends a signal to the brain, where then a gland called the pituitary gland is stimulated to secrete a hormone called oxytocin. Oxytocin, in turn, is secreted into the bloodstream and carried to the uterus. And oxytocin does something really interesting at the uterus. It stimulates muscle contractions at the uterus. The muscle contractions of the uterus pushes the baby's head against the cervix even more. This leads to more oxytocin being secreted, which leads to even stronger contractions, keeping a positive feedback loop going where the events amplify and the contractions just get stronger and stronger and stronger as the amount of oxytocin in the bloodstream increases and the severity and the frequency of the contractions increase. Sometimes this can happen over the course of a few hours. Sometimes it might take a day even, but eventually the stimulus will disappear and the positive feedback loop would end. So what causes the stimulus to disappear? The baby being born. Once the baby is born, the head of the baby will no longer be pushing against the cervix and oxytocin production will stop. So that's a positive feedback loop. Positive feedback does not lead to homeostasis. Homeostasis is all about maintaining the set condition. So let's talk about then one example of a negative feedback loop in the human body that leads to homeostasis. And let's start with one of the examples that you might find most familiar, which is the process called thermoregulation. This is the ability to maintain a constant internal body temperature. We've alluded to this process a little bit in a previous slide. Let's just talk about it in a little bit more detail. And so let's just talk about the difference between ectotherms and endotherms. Not all animals undergo thermoregulation the way that we do. You've probably learned a little bit about cold-blooded versus warm-blooded animals in grade 11. For example, cold-blooded animals or ectotherms like fish, amphibians, and reptiles, they are not able to control their body temperature the way that endotherms can. So their body temperature is mainly dependent on external heat sources, which means that their body temperature rises and falls pretty much with the surrounding environmental temperatures. So they have a very, very wide set point of temperature ranges that they can survive because they don't have the ability of maintaining homeostasis and thermoregulate, at least not to the degree that we do. Endotherms, on the other hand, birds and mammals, or warm-blooded animals, are able to maintain constant body temperatures. In order to stay alive, our cells have to stay within a fairly narrow temperature range. So we have no choice but to thermoregulate. So if it gets colder or if it gets hotter, our body temperatures may fluctuate, but within a very narrow range. So let's take a look at what happens when it gets hot outside. The stimulus would be an increased body temperature above the set range. And so we'll say the set range is 37 degrees Celsius. It's a hot day. Our body temperature has risen above 37 degrees Celsius. So that's the stimulus. Remember, the first thing that happens is you have a sensor. So somewhere in our body, our skin, we're going to have the ability to detect that body temperature. Our control center, which is a region of our brain called the hypothalamus, which is our brain's thermostat, can then compare that set temperature to the temperature that sensors have detected. The sensors would be nerve cells within our skin, and it's going to realize that the temperature is above the set temperature. So then there's going to be a few things that the brain is going to do in order to reestablish homeostasis. The first thing that's going to happen is a signal is going to be sent to one of the effectors, and one of those effectors is the sweat glands. It's going to induce sweating. So we have now increased sweating, especially on our skin, which is going to lead to heat dissipation via evaporation. Another effector will be something called vasodilation. Vasodilation will happen at the skin blood vessels. So what vasodilation means is that blood vessels will dilate or will become bigger, bringing more blood to a particular area. And in this particular case, blood will be drawn by vasodilation towards the surface, towards our skin. So we will turn red as more blood goes to the skin surface. Our skin will feel hot, will become flushed. But what that does is it basically brings a lot of the heat from our body, which is carried in our blood, out into the surface so that it can be dissipated into the atmosphere by a process of radiation. And then last, Another factor could be behavior changes. The brain can also cause us to change our behavior in response to those raised body temperatures. So we might seek shade, or we might remove some clothing so that we can feel cooler. So all three of these effects are then going to drop our body temperature, hopefully to the set conditions of 37 degrees Celsius. Once that happens, sensory nerves that are going to detect that change in temperature are going to send a signal to the control center, and the control center then can stop the effectors. That can stop our sweating, it can stop vasodilation, can maybe change our behavior accordingly, and the loop will only reestablish itself if body temperature once again raises above. And so that's one part of thermoregulation. Now, sometimes our body's not able to reestablish the set conditions. And this is when we can get into situations where we can end up with something called heat stroke. Heat stroke is actually something that can be very dangerous. Obviously, it happens more often in the summertime. Children, seniors have a lesser ability to thermoregulate, so they're more at risk. Athletes, people who work outdoors, will also be more at risk for heat stroke. And heat stroke is what happens when our body just loses its ability to reestablish our set temperature via homeostasis. The signs of it can include sweating stopping. Like, we sweat when we're hot, but when we hit heat stroke, we stop sweating. Our skin gets dry, hot, and red. There's dizziness and headaches, vomiting, constriction of our pupils, unconsciousness, and so on. And so there's a few things that you can do to help someone if you think they have heat stroke. Obviously, it's a life-threatening condition, so somebody should be brought to an emergency room. But until that can happen, you can always move a person into a cool place, away from the direct sunlight, elevate their feet, use cold compresses, so cold towels that are damp or ice, and you can put a fan close to them so you can lower their temperature and definitely keep them hydrated. So these are some things that you can do for that. Okay, so let's talk about what happens then if our body drops below the set temperature of 37 degrees Celsius, or maybe even way below that. And so again, that's the stimulus. Again, sensory receptors in our skin will detect the drop in body temperature and will send that information to the control center, which is the hypothalamus in the brain, which is the thermostat. Now, again, there will be three effectors. The first one will be shivering. So sweating happens when we get too hot. Shivering is what happens when we get too cold. The response basically is to increase rapid muscle contractions in our skeletal muscles, which in turn increases our temperature through cellular respiration. That rapid shivering, that rapid muscle contraction, is going to use a lot of ATP energy. And as you learned in the unit on cellular respiration, you learned that our body's ability to both produce and use ATP is not 100% energy efficient, which means that every single time there's an energy conversion in our body via the production of ATP or the use of ATP, we're going to lose some of the energy as heat. And so the shivering is going to generate heat, which in turn hopefully is going to warm up the body and increase the body temperature. Another effector is going to be the opposite of vasodilation, which is vasoconstriction. So vasoconstriction will happen in our extremities and our skin, and in order to essentially conserve body heat by limiting the amount of blood that goes to the outside of our body or to the surface of our body, in order to prevent some of that body heat to dissipate into the environment. And this is why certain body parts are more likely to undergo frostbite before others, because there are some body parts that are basically vasoconstriction happens even stronger. These are body parts that are essentially deemed to be less important. So for example, the tips of our noses, our ears, our fingers, and our toes, those areas, vasoconstriction happens more strongly there in order to conserve body heat, which also means that those are the first places that tend to get frostbitten. And the third effector is once again a change in behavior. You might seek shelter, you might add more clothing, and so on. All three of these hopefully will then result in the body temperature returning to the set point, which would then send a signal. Sensory nerves will send a signal to the control center in the brain to let the brain know that we're back in business, we're back at a set point, we can stop the shivering, we can stop the vasoconstriction, and so on. If the body temperature drops well below 37 degrees Celsius, if the conditions outside are too extreme, then we can enter something called hypothermia. And hypothermia basically happens when our body temperature drops below the set point. Early symptoms of hypothermia would be shivering, fatigue, loss of coordination, sometimes confusion and disorientation, which can make things dangerous, especially if someone is lost outside, and that's why they're becoming hypothermic. It could actually lead to a person not being able to make good decisions that would save their lives. Late symptoms of hypothermia happens when the person stops shivering altogether, skin turns blue, pulse rate and breathing rate slow down, and there's a loss of consciousness. And here you can also have some first aid things that you can do in order to treat a person with hypothermia: moving the person to a warm place, removing any wet clothing, warming the center of the body first, the chest, the head, the neck, and the groin, giving warm beverages, wrapping them in a warm blanket, and of course, administering CPR if necessary. Pretty much all of our body systems play a role in some way in maintaining homeostasis. In the previous examples that I just gave you with just thermoregulation, we saw that the musculoskeletal system was involved with shivering, the integumentary system, which is basically our skin, was involved with the production of sweat by sweat glands. There was vasoconstriction and vasodilation, so the circulatory system was involved. A lot of our body systems work together in order to maintain homeostasis. But we definitely do not have the time to get into every single body system for this unit. Usually what we do in this unit is we focus on the hormones. We'll talk a little bit about how we control our blood volume and urine output. And then last, we'll finish up with the nervous system. And so this will be the focus of this unit. So this is it for today's lesson. Talk to you soon.